Today we will cover an important topic, which is Go concurrency. Concurrency is powerful because it allows us to run multiple parts of a program at the same time. It's used by great tech giants like Google and Uber. And after this tutorial, we will get to create our own app using Go concurrency. It will be a live chat app, so stick around and make sure to hit follow so you don't miss the next tutorial. Let's say we have this simple function that just prints out the value of I after each iteration. The way we know about programming is that we are sure that we won't be requested to insert our input when the loop did not break, right? So let's run this. Let's slow it down a little bit by adding sleeping. No matter how many times I press enter trying to insert something, it will never break the loop. Sometimes having such a long function, or let's now call it a thread, can be a big waste of time, because you can finish some other quick task, like this scan here, while the other one is still iterating. And to do this, we would like to run the two tasks or threads at the same time, or more precisely, concurrently. To do this in Go, let's wrap this part in brackets and add the word go before it. Now we have two different threads. Technically, we have two threads here because main is also a thread. It's actually the main one, like the name suggests, and it's keeping the other ones alive. The other ones are child threads, we can call them. Now, if I run this, and let me just increase this 3 seconds so I have more time to show you that the other one is also running. If I enter hello here, the loop will break. So what happened here? I told you that the main thread keeps the other one alive. And since the main has finished its job, kinda, the program will end, including ending the other ones. If I add another thread, the three of them will be running together. As you can see here, the three run together. And did we precise any order of which one could start first? We didn't. This is why here we have B1 starting before A1. And as soon as I add an input at the main thread, they will all terminate before reaching 5. If the main thread was accepting 2 inputs, I can insert hi in here, but it will not terminate the other because the main still has another line to be executed. If I add my second input, now it's terminated. I just want to mention quickly, without getting into any details, that the threads do not run at the same time. But every time the OS starts running one thread, then stops it and schedules another one to run. And I also want to mention that I can call any function as a Goroutine. If I take this piece of code here and name it printer, then we just start it this way. Okay, one important concept about concurrency is resource sharing. As one of the use cases of concurrency, it is the same as online docs collaboration, where you'd be all collaborating on the same document and thus changing same resources at the same time. To keep the things right, we have to keep the data consistent. Let's take this example. I have a variable sum, and I will create a function that adds to sum. And let's call it twice, to add 3 and 5. So I know that the expected result should be 8, right? But we cannot guarantee that. Because what you see here as just one instruction, in reality it's a couple of instructions. Under the system will copy the value of sum in some temporary memory, add 5 or 3, because we didn't mention any specific order, and then recopy that to the original memory slot of sum. What could happen here is before it copies back 3 to the original memory slot, the scheduler could decide to run the other one and say it finishes running at 5. Now we go back to the other thread. What will the system copy back? Well, we left the instruction where it will copy 3 back, and it's exactly what will happen. So it will override the 5 with 3, and we will never get 8. And this is one of the many possibilities. We could of course have a correct result, but it is not guaranteed, and we call this behavior undeterministic. And so it is our job to make it deterministic. So one solution to this could be, let's not give that resource to the other thread until the first finish using it. Let's lock that resource specifically. And this mechanism uses an abstraction called locks that we can import via sync package. You can find all this information in the description below. Most of them are from the official Go documentation page, so you can check that out too. So when I wrap a shared resource around a lock, there is no other thread that can access that resource unless the lock was released. So let's try this here. Wrap sum between lock and unlock. So now the lock will not be released until the sum contains 3, no matter how many instructions are present under the hood. To make sure this printing instruction only happens after both threads finish, let's have the main sleep after calling the second add. I think 3 seconds will be enough. Let's take the previous case scenario and look at how the execution could go. So add 3 has the lock, it copies and add 3, and before finishing, it's interrupted. Add 5 starts. It will try to get the lock, but it cannot, so it stops here. We go back to 3, it will finish execution. Let's copy back 3 and release the lock. If we go back to 5, it will try to get the lock, and it can now because it's available, so everything is executed correctly. So now we cannot just assume that these instructions will take 3 seconds. We need a better mechanism for this. And we can achieve this by using something called a wait group that will tell main, okay, wait for these 2 before starting. Add is for the number of threads I have to wait for, which here is 2. Then, when a thread finishes, it will signal by calling done. And if you're familiar with defer, it means this will be the last instruction to be called. And it makes sense that after all the other instructions, done should be called last. Even for the unlock, we can use defer. It's the same logic in here, that it should be called last. I would still say that using defer with unlock depends on the type of thread you have and your logic, but just to get the idea behind defer. Now I can remove all that and simply tell main, okay, wait for them to finish. And it just works. Now let's see another concept. Say I am now allowed to run main if one of the adds is finished, or I don't know how many threads are running and I want to run main after a specific condition. So this can be done via condition variables. And the condition variable is specific to each lock, because as long as the condition is not satisfied, that thread cannot grab the lock in case it is going to use it for something specific. So say here, main will also do some changes to sum, but I want these changes to happen after sum is greater than 8. So from what we have just learned, is main should grab the log, so the values are consistent, and it should check for the condition. The condition here is not satisfied, so we will have to wait. And under the wood here, wait releases the log, so other threads could use it, of course. If it holds the log, then no other thread can change the value of sun, and will be blocked here forever. And who here is telling that thread that we are done? It's the child thread. And that's condition variables. Now, as the last and best, I would say, feature about Goroutines is channels. As mentioned here, channels are used to communicate between routines. Or the way Go creators would say it, do not communicate by sharing memory, instead share memory by communicating. So let's create a channel by typing var c as the name of our channel, chan, and channels have a type too. They can be a string, an int, boolean, etc., holding the value to be communicated between the threads. Let's create two threads, call the first pinger and the second printer, and they both take our channel C. And let's keep our main alive by adding a scanlan. Our pinger will just keep assigning the value ping to the channel. By using this arrow towards C. Printer will get the value from C to the variable message and print it. And Go channels also manage synchronization between the two threads, because as long as the printer channel did not consume the value in C, the pinger cannot continue, and vice versa. Means here, when pinger stops producing values in C, printer will stop. And this is a very powerful feature of Go. To highlight the blocking here, if I put a delay on the pinger, we will see it on the printer. And the same channel can hold different values, of course, depending on who uses it. Let's here add another thread, let's call it a pinger. So each time the value of C gets consumed by the printer, either of these can insert a new value into C. If we execute it, we see ping pong in here. Again, ping pong is not a default way of things getting executed. Let's have pingers step a bit. Now sometimes we get to see pong twice in a row because printer consumed the value and ponger is again available and can insert that value another time into the channel. And this is it about Go Concurrency for today. We will next build a live chatting app using all we learned from this video, so stay tuned.